All right, let's begin. Today we're going to try to do all of chapter 4. Hey, a lot of work. Before we get started, the reason I know Brandon and Brittany are just down the hall is because they came to my office for help with the homework just a few moments ago. And Brittany asked me about, I think it was 363. If she comes to class. Janice, were you sick or?
Sorry?
Were you sick on Monday?
Oh, I was out of town for the weekend. I didn't get back in time.
I was worried. I was going to call you, and I was like, well, I'll give her one day. Here they are. So which problem was it you asked me about, Brittany? Was it 63? Okay. In that problem, you have a person, a young lady, who is pulling up with a rope on a mass. And it tells you that she's pulling up with a force of tension of 50 newtons and that she raises it for a distance of 0.4 meters. Does that sound right? Now there's one more word in the description that's really, really important. It says that she lifts or whatever steadily. What would steadily mean? Nice job, Hannah. A constant rate, a constant speed. If it's a constant speed, what does that tell you about the situation? It's yes, it's an equilibrium. You have to have that process in your mind or you can't solve the problem. So if it's an equilibrium, what does equilibrium mean? Equal means equal. Librium is forces. The libra is force. So that's equal forces. So the sum of the forces, if you add all the forces up, it's equal to 0. So now let's look back at our picture. One force acting on that box is the force of tension that's pulling up. There's only one other force. And what's that one other force? The force of gravity. So with that identification, I'm actually going to answer the second part of the question first, because the second part of the question is wrong. And once again, I copied exactly from the textbook. The textbook is wrong too. So if I take this, the sum of the forces is 0, and I've got my forces drawn. So let's just apply it. So applying equilibrium, I'm going to have, looking at my forces and considering up positive, then I have force tension is up and force of gravity is down. Yeah, I'll put F sub G here. And I'll bet every single one in this classroom can solve this equation for F sub G. Right? Y'all should nod. Yeah, I can do that. I can do that. So this gives me force of gravity, which is equal to mg, is equal to force of tension, which is then mg is 50 newtons. And if mg is 50 newtons, how much is m? Yep. And so m is going to be 50 newtons divided by, using the textbook's number, they use 10 because it's easy for math, divided by 10 meters per second squared is equal to how many kilograms? 5 is not equal to 10, it turns out. That's why the problem, it's wrong when it says show it's equal to 10. If you show it's equal to 10, you made a big mistake somewhere because the mass has to be 5 kilograms. So that was the second part. That's one of the two things you have to do. What's the other one? The other one is to calculate the potential energy after she's lifted it 0.4 meters. So what's the equation for potential energy? MGH. Well, we just worked out that mg was 50 newtons, the last black line, mg equaled 50 newtons. So that's equal to my 50 newtons multiplied by the height she lifted it. And that's 20. What should the units be here? Joules. It's a newton times a meter, and a newton times a meter is a joule. I wanted to work the problem out because it has a problem, and of course, when there is a mistake in a problem, it can lead to much consternation in the students when they're trying to work it out and they're getting a different answer. Like, I don't see how it got that answer. Yeah, well, because they made a mistake, apparently. And here I let you in on a secret. Who writes the solutions for these? No. Well, I do the ones you see. But like the numbers that are in the back of the book, I didn't do those. Or the number in the question. It was done by some graduate student. When I was in graduate school, one of my professors was writing a physics textbook. And a graduate student was just hired to work out problems. That's what he did all day, was work out homework problems for the textbook. And so it's not like some master per se has done this. Yeah, Casey.
Does that mean that we get 10 extra credit points?
No. But it was a good try.
It said that in the syllabus that I wrote.
That you wrote. I was like, yeah, not the one I wrote. Any other homework questions? Yeah. Okay, Larissa. Quick on the draw.
The 2.59 with the horse and the guy. Yes.
Let me bring it up so I can actually see the problem. Actually,
The book had a very interesting response.
if I'm going to be smart, I'll bring it up here so we can all see it. Wouldn't that be the smart way of doing it?
Wait, which problems did you say?
259.
Does anyone remember which number that was?
Number 4.
While I'm here, while I'm here not going into the class, if we look down here at homework 1, just to make sure I point out to you, but want to make sure you see it. Homework 1, you can see now the solution is there. And you'll see things like I disagreed with the textbook here on if chlorophyll makes grass green. You're going to be graded on your explanation. The hypothesis chlorophyll makes grass green is incomplete. It's missing one of the pieces. What were the 3 things the hypothesis has to do?
Testable.
Okay, it has to make testable predictions. It has to. Say, Brittany?
It has to be scientific.
Okay, it has to be based on scientific ideas. And the final and most obvious, it has to explain the observation. So when you look at this, chlorophyll makes grass green. There's no scientific basis given there. You need to have something about why chlorophyll would make it green, right? Otherwise, you're just random.
But if you know what chlorophyll is, like already.
Then you could say chlorophyll makes it green because chlorophyll itself is green, and but you would have to have more. That by itself isn't sufficient. It's a true statement. It's just not sufficient in my opinion. The textbook says it is. And so you're going to be graded on your explanation of why it is or isn't. Right, so you don't have to match me. Casey had a question?
So I'm just skimming through these. So according to your answers, all of them were wrong.
According to me, all of them are wrong, yeah. The second one is what we call pseudoscientific. It's taking A that's scientific and relate it to B when there is no connection between the two. But if you look at, okay, I use A and B. If you look at option A and option C, it doesn't tell you what the link is, and so it still falls in that same realm. You have to have what the link is, the scientific linkage. And, Earth rotates about its axis because living things need an alternation of light and darkness. It's pretty obvious that that's incorrect, but there's no linkage given. It's similar to astrology. astrology says that the position of the sun in the sky affects our lives, but there's no linkage that anyone knows of how the two would be related. Okay, so you can look through and see all the solutions here. Yay, fun. Okay, back to the question okay, so which one was I even asked about? I forgot the number.
Number 59.
59, that's 259. Okay, the strong man is pulled in the three situations shown, rank from least to greatest the amount of tension in the rope in his right hand, the one attached to the tree. Okay, so got that picture in your head? Unfortunately, with this software, I can't copy and paste very easily, I don't think. So I'll have to draw my own picture. So I have figure A. I have a tree.
I think A was a two
Oh,
horses.
8 horses.
Oh, A was 2 horses. Well, I am already on a roll, baby. Must be butter.
Nice.
That's a perfect horse. Thank you. Thank you very much. I don't know why you guys mock. Here's a better horse, okay? In between, okay, there. Good. We're all quiet now. Horses have a rope tied to them. Each one's pulling. B, I'm sure has a tree.
Yes. 3 with 1 horse.
Tree. One horse. Man. Rope. And C, 2 trees. I know. 2 horses. There's going to be a magenta horse with this one here. So here's the magenta horse. Man in the middle. Okay, got the pictures. Good? Now I think it says to make this assumption that each horse pulls with exactly the same force. So if we look at the top one, how much is the horse on the right pulling with? The same as the one on the left. So let's just assign a number to it. Let's say it's 100 newtons. So the horse on the right is pulling with 100 newtons. The horse on the left is pulling with 100 newtons, right? Which means what is the tension? What's the tension on each side? Okay. Well, if the horse is pulling on the rope with 100 newtons, then the rope is going to be pulling on him with 100 newtons, right? 100 newtons, and the tension left is also 100 newtons. Now here with the tree, if this horse is pulling with 100 newtons, how much is it pulling on the man? 100 newtons. Now if the man is being pulled with 100 newtons in one direction, but he's not accelerating, how much does he have to be pulled in the other direction? 100. Otherwise he'd accelerate, right? Because he's in equilibrium. So this also has tension right equals 100 newtons. Now here in the bottom one, once again starting on the left, what's the tension in each rope? So how much is he being pulled to the left? So how much is the rope going to have to pull to the right to keep him in equilibrium? Now, if we go back to what the question was asking, because of course I don't remember. Rank from least to greatest the amount of tension in the rope. So we just take those and go, which one's the least? Well, those two are the same. So going from least to greatest, I'm going to go A and B together, comma C. Right? A and B together because they're equal. You can't put A before B or B before A. It's just a nifty little problem to make sure we understand equilibrium and forces. Okay, 15 minutes into class. Yes, Carmen?
Number 8. Agreed. Seconded.
There's agreement on this. Okay. Number 8. I won't give as long an answer because we don't have much time. When a cannonball is fired, momentum is conserved for the system of cannon plus cannonball. Have you ever, anyone here ever fired a gun? Okay, we got a few people. When you fire a gun, you have the same thing. Momentum is going to be conserved between the gun and the bullet. So if you just have the gun sitting on the desktop and you pull the trigger, what's going to happen? Yeah, the gun's going to come back and the bullet's going to go forward. Which one is going to go faster, the gun or the bullet? The bullet. Why?
Has less mass.
Has less mass. They both have the same force because Newton's third law says the force of what happens inside the gun is you have gunpowder that undergoes a very rapid reaction to create a bunch of hot gas. And hot gas expands, so you have a high pressure gas because it's trying to expand between the bullet and the backside of the gun. And that gas then pushes the bullet forward, and with the same force, it pushes the gun backward. And so the gun gets pushed backward with the same force as the bullet, but because it has a bigger mass, with the same momentum, you're going to have a much lower speed. So the gun doesn't move as much. But of course, you might have seen those YouTube videos of people doing stupid things like holding a rifle in front of their face and pulling the trigger. You can find a video of that on YouTube. That's really unwise because, yes, the gun is going to come flying back. Now, the ratio of mass of the gun to mass of the bullet makes it so it's going to be going, 1/1000th or so the speed of the bullet. It's still going to be coming pretty quick.
Nice way to break your nose.
Yes. Okay, so coming to this, when a cannonball is fired, momentum is conserved in the system between the can and the cannonball. Would momentum be conserved for the system if momentum were not a vector quantity? So vector means direction. If actually, I have to think about this once more because that's weird to think of. What if it wasn't vector?
I think the answer is no then, because momentum is a vector quantity.
Yeah, because if momentum was just magnitudes, we just took the size of the numbers. When we put that force on it, one goes forward and one goes backward. They're both moving. You start at rest and you end up with both moving. If there's no direction involved, you clearly went from 0 to non-zero. But if it's vectors, you can have them add up to stay at 0. Does that make sense? Brittany?
Conserved? It wouldn't be conserved?
It couldn't be conserved because you couldn't stay at 0 if all the numbers were just positive numbers with no direction. What were you going to say, Brittany?
So does that mean that if there was a force outside of the system that acts upon either the cannon or the cannonball, then that means that would mean it would not be a vector quantity?
No. Because A causes B does not mean that B will cause A. Or that B always results from A. I could have A or C causing B. So if B occurs, it could be A, it could be C. You don't know the other direction. Okay, let us move on with the lecture. The legend of the falling apple. Everybody know about Newton's apple?
Oh, yeah.
Okay, let's talk about the life and times of Sir Isaac Newton, which is talking about history is bound to kill my time in the class. But Isaac Newton was a child genius. Have I talked about Isaac Newton before? About his upbringing? Okay, so he goes to school. I said child genius. Of course, I made that up. He goes to school, and he was not a good student. I'm not going to ask for show hands how many people here are not good students, but he was not a good student. Not because he wasn't smart. Why do you suppose he wasn't a good student?
He hated school. His teachers were mean.
He hated school, his teachers were mean.
He had family problems.
He did have family problems. What, Candace?
Mine wandered.
His mind wandered. That's mostly it.
He got hit by a tree. Apple.
Casey, you got a lot of help.
Tree.
Okay, so he had family problems to begin with. He was born, and somewhere, I don't remember if it was before or after he was born, very close to his birth, his father died. And when he was about 2 years old, his mother remarried. But the man she remarried said, I married you, darling, but that ain't my kid. And so he didn't allow Isaac to stay with his mother, and so Isaac was raised by his grandmother. Yeah, that's real parental love right there. And so he's raised by his grandmother, and he goes to school, and here he is, this genius, and the teachers are boring him, just like I probably bored you, I have to admit. And he's like, I don't care about this. I want to learn about something else. And so he spends his time in class making little inventions, things to impress the ladies, which I kind of respect. It's not easy to make those little inventions. And so after he finished the compulsory education, they said, well, this dude is not made for school. Let's get him a job. So they found him a job as a shepherd. And a shepherd boy has but one job, to watch the sheep so they don't wander away. But what do you suppose that this little boy genius did when he was watching the sheep? He sat there and tried to make little inventions while the sheep wandered away. So he failed as a shepherd boy. And then, people said, okay, this guy is so smart, we've got to get him back into education. So found sponsorship to send him to higher education. And in school, just like Einstein, we'll talk about later, he was still kind of, I don't want to do what the teachers want to do. I've got real interest here. And our educational system, a lot of you are, probably all of you are education students. Our educational system isn't really made to handle students who are really motivated in one direction. It's made to just take everybody and say, here's the box, you fit in it. Find a way. And so he was mediocre through college until he got to the last year. And I don't know about you, but with me, my last year in college, I realized, oh man, I'm going to have to go looking for a job. Or I could just keep going to school. That'd be kind of cool to keep in school where you have more learning and things to teach you. And so his last year in college, he got his act together, showed that he was a good guy. Got hired on as a house scientist by one of the professors, which today would be like being a research assistant for the professor. And so part of his job, he now got to teach classes and things like that. Except for, what he didn't like doing? Teaching. So, something happened that was the greatest thing to ever happen for Isaac Newton, and possibly physics. The Black Plague! Hooray! So they have the plague, and the plague is killing people. People are dying everywhere. And of course, they figure this has to be something that can pass from one person to another. Let's not keep all of our smart young people together so that they can all die together. Let's separate them so they have a better chance of survival. And so school was canceled for about 2 years. And so now, if it was me, school's canceled for 2 years. I'm on the first flight out to Huntington Beach to hang out with my sister. But Newton says, sweet mother of Mary, now I can study physics with nothing to interrupt me. And so he went back to his grandmother's house and he worked on his physics. And virtually all of his great work was done there in that basically 2 years where he didn't have school and all he did was physics. I know this resonates with everyone. That's what you would do, right? Yeah. So he came up with the 3 laws of motion that we looked at. The first one, the law of inertia. That things stay in constant motion unless something acts on them. The second one, Newton's second law, surprisingly enough, that the acceleration on an object is equal to the net force acting on the object divided by the mass of the object. And his third one, for every action there's equal opposite reaction, that says if I punch the table, it punches me back with exactly the same force, but in the opposite direction. But he also came up with a law of gravity. Now, this law of gravity that he came up with is called the universal law of gravity. Gravity acts everywhere. And the thing that was astounding about it is probably not what other people think. So, the story about the apple and the tree. Notice it says here legend. It probably never happened. Right? Just like Galileo dropping the balls from the Leaning Tower of Pisa, probably never happened. Albeit, if you go to England, you can go to a Trinity College and they'll say, and there's the tree he was sitting under, even though he wasn't there at school at the time. Or you can go to his grandmother's farm and they'll say, there's the tree he was sitting under. Since it probably never happened, I suppose it doesn't matter if it's the wrong tree. And it's, I suppose, kind of like if you go to the Holy Land, you can see, this is the tomb where Jesus was buried. No, this is the tomb. So the story was to illustrate a point. And so the point is, you have an apple in the tree, and we can understand that something's pulling the apple down. But once it breaks away from the tree, there's nothing touching it. And people had thought that you really need to have contact for a force, right? I can't sit here and say, okay, I'm going to punch Hannah. Boom! Right? I can't do anything to her. I have to come over and actually make contact. And he said, well, as the apple's falling, there's something pulling it down because it's speeding up. Galileo had already established that it would be accelerating. And so he said there must be a force, according to his Newton's second law, to make it keep accelerating. And so that force would be the force of gravity. So he established that gravity is a range, has a range, and it doesn't require contact. And so the whole story about the tree is to illustrate that you have force when there's no contact, just over a distance. And so he has this equation for force acting over a distance called the universal law of gravitation. And so that force should be affecting other things, like there should be a force of gravity between the Earth and the Moon. Well, if there's a force of gravity between the Earth and the Moon, just like the force of gravity between the apple and the tree and the Earth, what should happen to the Moon? It should fall to the Earth. So then he has another question to answer. Why isn't the Moon falling to the Earth? And he said, well, okay, let's take this ball. I roll it off the table at slow speed. Where's it going to land? On the floor close to the table. But if I roll it out with a high speed, where's it going to land? Lands way out there. So if it's moving faster, it's going to fall. If it's moving faster, it's going to fall farther away. Well, believe it or not, it was established not only that the Earth was a sphere, but even the size of that sphere long before the birth of Christ. Like 200 years before the birth of Christ, it was known that the Earth was a sphere. Now, here's a question for you. If it was known 200 years before the birth of Christ that the Earth was a sphere, what in the heck was going on with Columbus? What's the common myth they teach you about Columbus? That he thought the world was a sphere instead of flat, and so he proposed an alternate route to sail to India. And that's when he got to, well, the Americas, let's say, because it was what, Caribbean Islands, I think, first or something like that. He proclaimed these people are Indians because I must be in India. He knew the world was a sphere, but so did everyone else. Everyone with education knew the Earth was a sphere. Where did the idea that the Earth was flat come from in this story? In the 1800s, I think it's Irving Berlin or something. It couldn't be Irving Berlin. Somebody Irving. Irving Berlin is like the guy from White Christmas, right? But somebody Irving wrote a story and pretty much just made up. And everybody thought the Earth was flat. And he said, no, it's a sphere. So in reality, he knew it was a sphere, everyone else thought it was a sphere. What he actually disagreed with was the work of Eratosthenes that gave us the radius of the Earth. He said, that's wrong. I think the Earth is much smaller in radius, which means the distance would be shorter going the other direction because, he basically miscalculated where India was because he thought the Earth was smaller. So if it's this far this direction, it must be only this far this direction. So, we knew it was a sphere. So since the Earth is a sphere, If the moon goes fast enough, it falls toward the Earth, but the Earth is curving away. And so it just keeps going around the Earth, constantly falling toward the Earth as changing its direction, but never actually getting closer to the Earth because of its motion. So what is this equation that he came up with? There it is in its glory. Force of gravity is G, where G is just a constant, just a number. On tests, the equations and the numbers will be given to you, so it's not like you have to memorize these, but you have to know what they mean and how to use them. So it's that G multiplied by mass 1 multiplied by mass 2 divided by the separation between the centers of the objects squared.
Whoa.
So let's, yes. So let's put it in practical sense. First, the force of gravity is always attractive, never repulsive. And the force of gravity acts between any two objects that have mass. So I have mass, you have mass. Newton's universal law of gravity says that there must be a force between me and you. Is it attractive or repulsive?
Attractive.
It's attractive. So I'm pulling all of you up here. And that force is proportional to my mass multiplied by your mass. So let's say my mass is 100 kilograms and your mass is 50 kilograms. So that would be 100 times 50 on top. Divided by the separation squared. So just taking Hannah as an example, because she's about 2 meters away. Let's say she's 2 meters away. Divided by 2 meters squared. Divided by 4 meters squared. 4 units of meters squared. And then multiplied by G, and that gives us the force. Now here's a simple question. How many people feel the force? Nobody? You don't feel me pulling you? You know, I am pretty heavy. Still don't feel it. Why not? Well, if you take the numbers that I just used, it's going to be 6.67 times 10 to the minus 11 newtons per meter squared, kilograms squared, multiplied by my mass of 100, your mass of 50. 100 times 50 is 5,000 kilograms squared. Divided by the separation squared, using my number with Hannah, it was 2 meters. 2 meters squared gave me 4 times meters squared. If you multiply that through, 50,000 divided by 4, that would be, or not 50,000, 5,000, divided by 4 would be 1,250. 1,250 times 6.67 times 10 to the minus 11. What does it mean times 10 to the minus 11?
It's like a small decimal.
Yeah, it's a very small number. You take that 6.67 and you move the decimal point 11 times to the left. So you have 0 point, and then you're going to have 10 zeros, 667. We multiply that by 1,250. Let's round it to 1,000. Let's round that to 7 and my number to 1,000. So 10 zeros and a 7, but then we have 7,000, so we have to move it over 3 places. We'd have 7 zeros and a 7. Or 7 times 10 to the minus 8. So that's approximately equal to 7 times 10 to the minus 8 newtons. I'll actually do the real calculation just so we can have the real number. 6.67.
Where does that number come from?
Which number?
6.67 times 10 to the negative 11.
It's a constant. It's an experimentally determined constant that's always that number. Times 5, 1, 2, 3, divided by 4. So the true number is actually 8.3 times 10 to the minus 8. That's the true number. 8.3 times 10 to the minus 8. Can you feel it? That's way too small a force for us to feel. For comparison's sake, this mass here is 20 grams. So it's going to have a force of 0.02 times, let's round to 10, is 0.2 newtons for this. So it's this divided by 1,000,000 roughly. 1/1,000,000th of this you're not going to feel. So that's why you don't feel that force of attraction between us. But it's there. It's just really small. Why do we feel the force of attraction between us and the center of the Earth? The Earth's mass is immense. It's, I actually don't remember its number, but it's somewhere in the ballpark of 10 to the 27 kilograms. I think that's right. And so you have that 10 to the 7 kilograms on top multiplied by g 10 to the minus 11. That's still going to give you something in the ballpark of 10 to the 15 or 10 to the 16. And then you multiply by our mass and divide by the separation between us and the center of the Earth squared. The center of the Earth is many meters away. But that mass is just so large that it still gives us reasonable sized forces. So now going back to, Larissa said, whoa, can you go slow? The force of gravity is proportional to the mass of the two objects multiplied together. So if we have objects with bigger masses, the force of gravity is larger. Which totally makes sense because everybody understands the force of gravity, and I'm standing here is the weight. And my weight is larger than your weight because I have more mass. I know Casey would say, awkward. But it's the truth. So we understand that part. The bigger the mass, the bigger the force. And the fact that we can feel that force between us and the Earth and not us and the other people helps us once again to understand it's both masses that come into play. And that's divided by the separation squared. So if you make things twice as far apart, what happens to the force of gravity between them? So if I go from, let's say I have force equals 1 Newton equals G M1 M2 over 1 meter squared. What would I get if I changed it, same M1 M2, but I changed it to 2 meters? Okay, 2 squared, what is 2 squared? 4. So it's going to be 1/4. I couldn't hear if you said 0.25 or 0.5. So, okay, but it would be 0.25 newtons. It'd be 1/4 as much if you doubled the separation. How about if you tripled the separation? 1/9, right? So the force of gravity drops off quickly with distance. We call it an inverse square law because of that. So inversely proportional because it's 1 over, and then the square because there's a square there. Okay. Already talked about that. Let's do our first clicker question. Yes. Newton's most celebrated synthesis is of, and I haven't used the words here about what's most celebrated. So this is, you don't have the answer laid in front of you. It's one to think about. But do answer. Maggie, Hannah, Jackie, Vanessa. And there's Raquel. Maggie and Vanessa. Now just me. There we go. Okay. We had 1, 6, 10. I changed the color so I'd be able to read them. You notice that? Yeah. Okay, so we had the biggest one was masses and distances. Now, I'm not going to have somebody answer this because I left this question out. The questions are pre-made for me and I can change them or whatnot. I left this one as is because I wanted to talk about it a little bit. Newton's most celebrated synthesis, the correct answer is earthly and heavenly laws. That's really the correct answer. It's true. Newton's big thing for science, of course, is the earthly laws. That is the laws of the three laws of motion we talked about, the universal law of gravitation. He also did some work in optics. He also invented calculus because with his three laws of universal gravitation, he realized, hey, I can't solve the problems. There's no math in the world that can solve my problems. And so he invented a new type of math called calculus to solve his problems. Pretty brilliant dude. But he wrote more about theology, about the heavenly laws, than he did about science. He wrote a set of Bible commentaries that I am told, I've never read either. I've read the encyclopedia, but not Ellen White's Bible commentaries. But they're very similar to Ellen White's in the theology. So he spent a lot of time in theology. He actually also dabbled in politics. He was a member of parliament, and he is on record as speaking once in parliament. He'd been there for a couple of years and hadn't said anything. Finally, he stands up to speak, and everybody's like, oh, what is the great man going to say? And what he said was, it's a bit drafty in here. Could we close the window? He was quite the politician, apparently. So I had this question here because I wanted that we think about. Today, we often have people who think that science and religion are just incompatible. That scientists science these days takes the approach that everything has to be natural, that there can't be a miracle. Where does that leave God if there can't be a miracle? It pretty much leaves him out. That life had to start without God because that would be a miracle. There couldn't have been a worldwide flood because that would be a miracle. And so science tends to exclude a lot of our Christian things. But it's good to see that some of these great men like Newton, they very much believed in Christianity. I can get past those quickly. Here's what the inverse square graph looks like. If you move away from the Earth, the force of gravity between you and the Earth follows that magenta line. As you move away, it drops off very rapidly. When you get farther and farther, it's very weak, but it's not dropping as fast anymore. So if you're out there somewhere, in the International Space Station, which I think is about here, is gravity acting on you? Gravity between the Earth is acting on you. In fact, gravity between you and the Earth, I put it a little too far because it's somewhere about 80%. 80 to 90%, somewhere in that ballpark, is the force of gravity on you when you're International Space Station compared to the force of gravity on you right here on Earth. Well, that brings up a funny thing because from everything we've seen on TV, watch the NASA channel, something that's science-based, not, science fiction like Gravity or... Is Gravity the crazy one where they basically have Sandra Bullock by herself the whole entire time? Yeah, that was pretty crazy science fiction. If you watch something like that, it portrays this, but also NASA, if you watch live telecasts of astronauts, when they're inside the International Space Station or inside an orbiter, they're weightless. But if the force of gravity is like 80-90% of what it is on Earth, how in the world can they be weightless? It doesn't seem to make sense, does it? But we have to define weight. Okay, let's answer this one real quick and then move on just so we can say we answered it. If the masses of two planets are each somehow doubled, force of gravity between them, does what? Answer quickly.
I'm just saying that I basically just wrote this question as my question.
Oh, so sorry.
I mean, not in so much.
always weird when I'm on those questions.
Okay, I move on in 5 seconds. Okay. Wow, we had a lot of variation here. I know I am taking a more than 50% problem or chance of a person having a wrong answer because less than half the class answered one answer. But Maggie, what was your answer and what was your reasoning? Well, which one was your answer? Okay, you chose A. And what was your reasoning? Why did you pick that out of the others? Okay. Well, if we look at the equation, the force is G. What can you tell me about G? This is to everybody. What can you tell me about G? It's constant. So G isn't going to make a difference. And we have divided by, I put R here. Our textbook used D. I probably should have put D to be consistent with the textbook. The distance between them squared. Well, did we change the distance? No. So for this problem, that stayed the same. We're left with mass 1 times mass 2. What happened to mass 1? It doubled. So if it doubled, I'll just write this. My force of gravity 2 is equal to G times 2 mass 1. What happened to mass 2? Also doubled. What's 2 times 2?
4.
And so, what was the correct answer? It quadruples because we had times 2 for each of the 2 masses. Not just for one of them, but for both of them. Okay, now the definition for weight. Weight is the force exerted against a supporting floor or a scale. So I stand on a scale, it measures me my weight. If I'm just standing here on the scale, the force down on the scale is my force of gravity, right? And so how much does it have to push up? The same, the force of gravity. So if I'm just standing on a scale, it's going to measure the force of gravity, and that's my weight. But if you're in the International Space Station, it's orbiting the Earth. According to Newton, what's it constantly doing? It's constantly falling. You're inside, what are you doing? You're falling with the same acceleration. And so if you put a scale down there, you don't press on it because the floor is falling at the same rate you're falling into it. So you just fall together. You don't push on it, and that's how you get the weightlessness. So weightlessness doesn't mean no force of gravity. It means that your surroundings are falling at the same rate that you are. So an astronaut, weightless. You drive your car off a cliff, assuming no air resistance, weightless. You hit the earth, weight comes back. That's when it gets bad. That's why you have the joke, I'm not scared of falling, I'm scared of hitting the ground. Whatever. So now some more practical examples. You ride an elevator. So you step in the elevator, you're at the ground floor of the Dick building, and you press 5 to go to the top because you've got that kind of exercise at program. So the doors close, and what happens? It goes up. You started stationary, and then you had an upward velocity. What has to happen between stationary and upward velocity? Acceleration. What direction is the acceleration? Upward. So if the floor is accelerating upward, what's that going to make? And you're standing on a scale, okay? You're that kind of a dork. You're standing on a scale in the Dick building elevator, and what's the scale going to show as the elevator starts moving up? Heavier. Why? Yeah, it's got to accelerate you upward. It doesn't just supply force equal to yours. It has to be bigger than yours so you have an upward acceleration. So your net force is upward because your acceleration is upward. Hence, the scale is pushing on you more. And so you're heavier while it's starting up. But then going from floor 2 to floor 4, it's going at constant speed. So you're moving up at constant speed. What's the scale going to weigh? It's going to weigh your normal weight. Because your acceleration is 0, you're in equilibrium. Your force of gravity downward is your normal weight. So the scale's going to push up. Then this elevator slows to a stop. What's happening during the slowing? Your acceleration is downward. And because your acceleration is downward, what's the scale going to read? Lighter. Now, because I'm out of time, when I was in graduate school, the students a year behind me, you know those little kids, so immature. They thought it was hilarious that everybody lie down on the floor of the elevator, and when it got down to the basement, they would all slap the floor, and then the doors open. You have all these people lying on the floor, pretend that the elevator had broken. Because, of course, if the elevator breaks, as shown here, you're weightless, you're floating around, it stops at the bottom, then you hit the floor with the thump that they tried to simulate by banging. Yeah, immature first-year graduate students. All right, I'll see you for lab